Hello and welcome to episode 9 of the Minimapper. Last time we talked mostly about mechanical constraints on the photointerrupter that I'm going to use. Today I'm going to talk about the electrical constraints and the circuit that we're going to use to deal with this thing. So the first thing to say is that we went through all this business with this spreadsheet for the mechanical constraints on the photointerrupters, and I ended up redoing some of that and changing the choice of photointerrupter, mostly because I remeasured some of the mechanical parts of this. In particular, I remeasured the thickness of the chassis plate, and it turned out to be a little bit thicker than I thought. And what would have ended up happening then is that the spacing between the PCB and the chassis plate would have ended up being only 0.5 millimeter with the photointerrupter that I was using before, and that seems like it'd be too little. It means you couldn't put any components on the bottom of the PCB. It means that there'd be a danger of shorting between the bottom of the PCB and the chassis, and it's just not very good. So I chose a different one. It's also made by Vishay. It's this TCST 1202. Electrically, it's the same as the other one. And it means that you can have a 5 millimeter spacing between the PCB and the chassis, which is much more reasonable. And you can see here that there's no mechanical interference with the motor. There's a little bit of interference with the chassis plate, but that's not a bother. And the optical path is fine. So the electrical properties of these things of these photointerrupters that are relevant, there are two sides to them. You've got the emitter, which is an infrared LED. So you care about the forward voltage of the LED and the forward current that you should use. As in most data sheets, they give typical values, but you should really design against the maximum or minimum values. So we can take a kind of typical value for the forward voltage of the LED, but make sure that things work for the maximum as well. The maximum forward current they specify is 60 milliamps, but a lot of the other characteristics and graphs in the datasheet are based on a forward current of 20 milliamps. So that's what I'll design to, 20 or 25 milliamps. It seems reasonable. On the phototransistor side, the things that you care about are how much current you get from the thing when there's light, when there's a radiation from the infrared LED is falling on the phototransistor, and how much current you get from the thing when there's no radiation. So the minimum value that they state for the light current is 1 milliamp and typical is 2 milliamps. But it's important to remember that because of the geometry of the motor encoder disk and the holes in it, we're actually going to be getting less than this. And if you looked at the calculations I did in part 8, you'll see it's about half. And we'll look at that in a minute, because we're going to use those things to drive some simulations. The dark current is quoted as being 100 nanoamps, and that's probably true if there's no radiation at all falling on the phototransistor. But in reality, there's always going to be some ambient radiation in the wavelength range that these things use. I think it's about 930 nanometers or something. And so you're always going to get a bit more dark current than this. So again, we need to design conservatively so that things will work regardless. So what we need to do for the circuit for this thing is pretty obvious. We need to distinguish between the dark current and the light current from the phototransistor, and we want to generate logic levels from this. High for light, low for dark. And that has a few implications. First of all, the phototransistor is a current device, so we're going to have to do current sensing, which means we need a resistor to turn that current into a voltage. Now, if you're doing this with a photodiode, which produces a much smaller current, then people generally use a thing called a transimpedance amplifier, which is a particular setup of an op-amp that turns a current into a voltage. In our case here, because we're using a thing that has a phototransistor in it, the currents we're dealing with are much larger. And so we don't need a transimpedance amplifier. We can just stick a resistor in there and measure the voltage across it. We do need a comparator to distinguish between the on and off states, and how we set that up is going to be most of the design work of this. So the questions are, what comparator do we use? How do we set the comparator threshold? How do we choose a threshold that guarantees that we get a high logic level when there's light and a low logic level when there's dark? Do we need hysteresis to deal with noise and switching? And how do we design things so that they work in the worst case of component choices? So one thing I wanted to do was some simulations to look at the behavior of this comparator that we're going to need. And to do this, you need to know something about the current that the phototransistor is producing. And the current that the phototransistor is producing depends on how much radiation it's getting from the infrared LED in the photointerrupter to the phototransistor. And so I thought to myself that it would be interesting to calculate the geometry of this to see how much of the radiation from the infrared LED the holes in our motor encoder disk let through. And so that's what this cartoon is about. If we start at the first cartoon picture up here, this red rectangle is supposed to represent the optical aperture of the infrared LED and the phototransistor. So this is a cross section of the beam of infrared radiation that goes from the infrared LED to the phototransistor. And these circles are the holes in the motor encoder disk. And this dashed arc is the line of centers of those circles. So the first cartoon here shows the situation when you have a hole in the motor encoder disk at top dead center, central on the optical aperture. And the amount of radiation that's being let through is basically this. So let me see if I can do that in a different color. Can I do that in a different color? Yeah, we'll do green. Oh, but that's not very nice let's try a different color again. Yeah. So basically this bit, this area, or the fraction of this area covering the whole of the aperture, gives you the fraction of the maximum light current that you would expect to see. And as the motor encoder disk turns, so it's turning this way, the hole moves off of the center line of the optical aperture. So this line here shows you where the center of the motor encoder disk is, and the other line is the vertical axis of the optical aperture. So as the hole moves on, this overlap area gets smaller, and eventually the hole doesn't overlap with the optical aperture at all anymore. So the radiation from the infrared LED is completely occluded, and none gets through to the phototransistor. And so what you can do is you can calculate what fraction of the optical beam is allowed through as a function of the angle the angle between basically the center of the motor encoder disk hole and the center of the optical aperture. And what you get is this curve. And I mean, it's not so surprising. The current that you get from the phototransistor is not going to switch on and off suddenly, because the holes in the motor encoder disk are going to gradually move across the optical beam. But what's important here is that this is quite a gradual transition up and down. And so we're going to need to deal with that. The details of the geometry of all this are done in part 8 if you want to do it. I mostly do this for my own amusement, but I think it's quite nice. And so what you can do with this is you can then calculate simulated current traces. So this plot shows, as a function of time, the current you'd expect to get from the phototransistor. And what's happening here is that the motor encoder disk here is starting from rest and is gradually accelerating here. And so you see, going down here, you have a first pulse, and then a second pulse, and the frequency of the pulses increases. And the whole of this simulation that I did, the motor encoder disk starts from rest, accelerates to a constant speed, and then decelerates to rest again. And you can see that I've added a little bit of noise, and that the current doesn't go to zero. I've taken a very, very conservative value for the true dark current of 100 microamps, which is huge. It's going to be way more than reality, but it's a very conservative estimate. And so what you can do with these simulated current traces is you can use them to drive LTSpice simulations. LTSpice has a way of setting up current and voltage sources with data files as input. LTSpice calls them PWL files, for piecewise linear. And I've seen quite a lot of examples with LTSpice where people do clever things with pulses and switches and things to generate arbitrary waveforms or semi-arbitrary waveforms. But this approach using PWL files means you can do quite sophisticated simulation outside of LTSpice and then import the data and use it to drive your simulations. So that's what we're going to do now. So here we are in LTSpice. We have a constant 3.3 volt voltage source over here that we're going to use to power some things. We have a comparator. The LT1017 is not what I'm going to be using, but it's one that's available in LTSpice. It has a model available in LTSpice, so it's convenient to use for this. The output voltage from the comparator is going to be either plus 3.3 or 0 at ground, so that'll be suitable for driving logic inputs to our microcontroller. One input of the comparator is set halfway between 3.3 volts and ground just by using a voltage divider with two 1K resistors. The other input to the comparator is driven by a current source across this 3.3K resistor. And the current source is based on that simulation that I showed you just now. It's a variant of this simulation without any noise in it, because I want to show you what happens without noise first. So this is one of these piecewise linear files. And basically, this file contains 8 seconds of data. And so when you run a simulation, this current source can play 8 seconds of simulated data. And the maximum value of the data, the current in there is about 1 milliamp. So with this 3.3K resistor, the non-inverting input to the comparator ranges from about 0 to about 3.3. So let's run the simulation and see what happens. Now things go a tiny bit funny here because I've got a few other LTSpice files open at the same time, and LTSpice doesn't like it very much. So we've done 8 seconds of simulation. Let's have a look at the current source first, and you can see it's just like I showed you on the plot just now. It starts off slowly, and then the frequency of pulses increases, and then eventually it slows down. So this represents the motor starting from rest, the robot starting from rest, accelerating to a constant speed, going for a constant speed for a bit in the middle here, and then decelerating to rest again. And now if we look at the output voltage, we see that it switches between 3.3 volts and 0. And it switches nicely, and it switches at about halfway up. And so that's kind of what you'd expect. And this blue trace, the output voltage, is a good input that we could use to drive our microcontroller. We can count the pulses and work out how fast the thing's going from there. So that's when there's no noise. What about when there's noise? So this one is exactly the same circuit, except that the PWL file driving the current source here has some noise in it. So if we run the simulation, again it's 8 seconds of simulated data, 8 seconds of simulation, and we'll see something fairly similar. So first of all, let's look at the current source again. The difference here is that it looks a bit fuzzy because there's some noise on it. Again, let's look at the output voltage. And superficially, at least, it looks okay. The thing's switching back and forth between 3.3 volts and 0. But if we zoom in, and you can see the noise on the current signal here, these transitions look suspiciously fat. And if you zoom in again, you can see that there are multiple transitions here. And what happens is that the current, the input current, and the voltage that's produced from it across the resistor R1 is wobbling around near the switching threshold here. So it goes below the threshold, then it goes above the threshold, below again, before it finally settles down to staying below the threshold. And this is a common thing with looking at any slow-moving or smooth signal with a comparator. You're always going to get this kind of spurious switching if you're not careful. And it's not something you can avoid, because if we zoom out and look at this, you can always slow your motor down enough that the slope of the rate of change of the current is slow enough that these little noise switching things are going to be a problem. And it can be a really big problem, because if you have these spurious pulses, if you're saying, okay, every pulse is so much angular motion of my wheel, then it'd be very easy to get right off track with your measurements. So you need to do something about that. And the classic thing to do with this is to add some hysteresis. And hysteresis basically just means making the threshold for transition in the output of the comparator depend on the current state of the comparator. So if you think about making a transition from high to low, let me draw a picture, say this is time, this is high, and I'll show this is the threshold. So the signal's doing this, and our output, which is high here, is going to switch to low here as the signal crosses the threshold. What we don't want to happen is for, if our signal goes up a little bit again, for us to suddenly switch again. What we basically want is for the threshold, when we're in the lower state, to be higher. We want the threshold to be somewhere up here, so that this signal would have to get up here for us to switch again. And vice versa, if the output state is high, we want the threshold to switch to be down here. And this pushing apart of the switching thresholds is what hysteresis is about. And the way we do it is we take a bit of the output and we feed it back to the positive, the non-inverting input of the comparator. So this is positive feedback. So the easiest way to think about what's happening here is to think about what the situation is if V out is 0. If V out is 0, then this point is grounded. This voltage is the signal based on the phototransistor current. But because of the voltage divider made by these two resistors, the voltage that we're applying here is only 32 over 33 times the voltage here. And what that means is that the voltage here is going to have to go further up to switch the comparator to its other state. So what we've done is we've pushed the transition, the threshold for the transition from low to high further up, which is exactly what we want to do. And you can carry out a similar analysis when V out is high, and you'll see that the threshold gets pushed down. So now if we run the simulation, we'll see something a bit different. And again, this is with the noisy data. So let's add the current trace. So you can see it's the noisy current trace. Let's add the output trace. And what you can see here is that the transitions are clean. I can zoom right in, and there's only one transition here, even though the input signal is moving slowly and has noise on it. Now there's some other features of this curvature of the tops that I'm not quite sure where it comes from, but it doesn't matter as long as, because we're going to be using the output of the comparator as input to a microcontroller input, as long as the high level here is above the normal logic level input for a 3.3 volt logic. So I mean the levels are usually something like this. Anything below about 0.6 volt is counted as low. Anything above about 2.7 volts, I think it is, counted as high. So we should be fine. So basically, I'm just going to duplicate this circuit in KiCad, and that's what we'll do now. Let's have a look at the circuit in KiCad. So here we've got our photointerrupter with the infrared LED in the phototransistor. This resistor value is chosen so that if you remember the typical and maximum values of the voltage drop across here from the data sheet, it's chosen so that if you have the typical value, you get 25 milliamps of current through here. And if it's the minimum value, you get, if it's the maximum voltage drop, you get 21 milliamps. So that's a pretty good range for what we need to do. On the phototransistor side, this resistor value is chosen to give a reasonable voltage at this node when the phototransistor current that we're getting is 0.5 milliamp. So the minimum light current from the phototransistor is 1 milliamp, but the maximum overlap between the area of the motor encoder disc holes and the optical aperture is about 1/2. So you actually end up getting about 0.5 milliamp at most from the phototransistor. And so this voltage is chosen just to be a reasonable level to make the comparator switch. And then the comparator I've chosen is this LMV331. It's cheap, single supply, it's from TI, comes in a SOT23 package. It's fine by me. The inverting input to the comparator is halfway between the 3.3 volt supply and ground, same as in the SPICE simulations. And these feedback resistor values for the hysteresis, positive feedback for hysteresis, they're the same as in the simulations. And you can work out how much the threshold levels get split based on those resistor values, and it's about 0.1 volt. So basically any noise at this point that's less than 0.1 volt won't cause any spurious transitions at the output here, which is what we want. So that's basically it for the photoencoder and motor encoder design. The next thing to do is the sort of integration part of this motor prototype board, which is sorting out power sources and the interfacing to the microcontroller development board I'm going to use. None of that should be terribly complicated. The most difficult thing next is to actually try and make some of these encoder disks that I want to use. So the next thing I'm going to do is the power and integration stuff, and that should mean that we can finish the schematic, move on to layout, order some boards, and put some stuff together and start doing some experiments. So next time it'll be power and connections. See you then.